So in chapter 16, we're going to talk about Earth's surface. Our outline is going to be principle of uniformity, diastrophism, stress and strains, folding, faulting, types of faults, earthquakes, tsunamis, origin of mountains, types of mountains, weathering and erosion, stream development, deltas, and glaciers. So we have this principle of uniformity which helps us to understand and interpret Earth's surface. The rocks that are changed today are changed by the exact same processes that changed them in the past. And that's the principle of uniformity, meaning what happened in the past is happening now. What we see now, we can use to infer what happened back then. And what we do know is that there's catastrophic events that will always contribute to changes on Earth's surface. So volcanoes, earthquakes, meteorite impacts that are catastrophic, meaning they are not part of the natural processes we're going to talk about. So diastrophism is the process of deformation, so the breaking down, that changes the Earth's surface. It's going to produce structures like plateaus, mountains, and folds, which are things we'll talk about in this lecture. Stress and strain. We kind of talked about stress and strain when we discussed elastic and inelastic materials back in physics. So the stress is the force that's tending to compress, pull apart, or deform a rock. And the strain is what's going to happen to the rock as a result of the stress. So whether the rock breaks, fractures, that's going to be a result of strain, but it's happening because of stress. You can see here we have uniform pressure, tension, compressional, shear. Looks a lot like our divergent, convergent, and transform boundaries. So we have to remind ourselves that sedimentary rocks are going to be the rocks that are broken down from other existing rocks or are made up of previously existing rocks. So sedimentary rocks are going to originate from flat sediment deposits, meaning when the sediment's laid down on the ground, it's going to be done so in a horizontal layer, and then those layers are going to form on top. They can be slightly angled, as you see here in the bottom image, but as you see in the top image, these are very clearly lines of sedimentary bedrock. Now, folds are going to be bends in the layered bedrock that we see here that are a result of stress producing plastic strain. So this is strain that cannot be undone. It's not elastic, but inelastic change. So when we have widespread horizontal stress, it produces unique features like domes, which are raised areas, and then basins, which are like bowls. So in a fold, we have two parts of a structure that we might be looking for. The first is the anticline, which is the arch-shaped structure that we see on the right-hand side, where the younger strata, which is the youngest layer, is going to be on the top, kind of like the mountain, whereas the syncline is going to be the trough-shaped. And you can see there, it's kind of like a part of half of a PVC pipe, where the younger strata or the younger layer is still on top, but it's in the shape of like a cup instead of a hill. So something else that can happen as a result of stress is faulting. So this is produced by relative movement on opposite sides of a crack in a rock. You have what's called the footwall, which the footwall, if we look at the image on the left, the terms originate from people who were in a mine, so underneath the bedrock. And the footwall is going to be the piece of the rock that's underneath their feet. So if you imagine a person standing along the fault line, the crack in the rock, what's at their feet is going to be the footwall. What's above their head is called the hanging wall because it's hanging above their head. And that's the mass of the rock above the fault. The fault plane is the surface between them, that line that you see right there. Now this rock you see in the bottom left-hand side, you should see hopefully that there is a white line with the red line next to it where they used to be connected. But over time the fault line formed and the rock either one shifted up or one shifted down. And so practice identifying the three features there in red, the terms, on this rock right here. And if you are confused or unable to, then please reach out to your instructor. So we're going to talk about types of faults. The first fault is a normal fault. So this is where we have a crack in a rock that occurs, and the hanging wall, so the one above your head, is going to fall down relative to the footwall. That's falling down because of gravity. So this type of stress is going to be essentially pulling apart two pieces of rock that have cracked. And because they've cracked, the piece that's the hanging wall is going to fall down, and it's going to result in the structure you see on A. Now a graben is going to be the same type of pulling apart action. You can see the arrows on either side of the image, but because there's two fault lines, there's two cracks in the rock, the middle section essentially is going to fall out, kind of like a sinkhole, and that's going to be the graben, where the block that's in the middle is going to drop down to a lower spot. Now, another option is a horst, and on the horst, we're still going to be pulling apart the rocks, but instead of the middle piece falling down, the two pieces on the side are going to fall down relative to the footwall and produce a higher area. Okay, so the graben's going to produce like what's a valley or a basin, and the horst will produce like a dome or a slight mountain. I can call it a big mountain. The other two types of faults that we have are reverse and thrust fault. So instead of pulling apart the blocks, now we're going to smash them together. We can see the arrows are pointing in. So when we put pressure on the outside of the rock and there's an existing crack, instead of the hanging wall falling down, it's actually going to be pushed up relative to the footwall. And that's because of the stress that's compressive. The thrust fault is the same type of compressional action, but the angle is very low angled. So instead of it producing a jagged feature coming up from the ground, it's going to produce a very small angled, okay? So the only difference is the angle of the actual fault line. So let's talk about earthquakes. The official definition of an earthquake is the quaking, shaking, vibrating, or upheaval of the ground. It's going to result from the sudden release of energy from stress on the rocks. So what results is strain. The adjustment is what we see. The vibrations are seismic waves. We've talked about waves in the last chapter when we talked about understanding the inner core of Earth and the outer core by using P waves and S waves. And these are kind of the same similar type of waves that we're talking about. But there are additional types of waves like love waves, Raleigh waves that are seen with earthquakes. So most all earthquakes occur along fault planes when one side becomes displaced with respect to another. But there are instances where earthquakes do not occur at fault lines. But most of the time, most all earthquakes occur along a fault plane. You can see an example of this road. It looks like maybe it was a bridge that fell from above, or could have been a highway, but you can see it's completely fractured apart. This building cracked in half and fell over. So earthquakes are definitely something that is not new to us. They do occur in the United States. The most common place for earthquakes is probably along the San Andreas Fault, which kind of runs right through California and Los Angeles. And so that's a place where we've had quite a few earthquakes in our recorded history. So the cause of an earthquake is thought to be what's called the elastic rebound theory. So two plates are tightly pressed together. The friction that occurs between the plates restricts the motion, but over time that stress is building up until the friction or the rock will rupture, and it's overcome with it, and it's going to cause the stressed rocks to snap suddenly into a new position, which that snapping of very large plates that everything is built upon causes the tremoring, the earthquakes. But we do detect small tremors all the time, but we normally don't call them an earthquake until it's measurable and detectable by people. But there are detected motion around fault planes all the time. So when it comes to locating and measuring earthquakes, there's two places that are most important. The focus is the actual origin of the seismic wave, and the focus is below ground. It's going to be along the fault plane, wherever that is, that causes the earthquake to originate from. The epicenter is what we normally fixate on. The epicenter is directly above the focus, but it's on Earth's surface. And this would be what we would call the center of the earthquake. It's probably where the most damage will occur if it's going to be in an area that's heavily populated. But the epicenter is on Earth's surface and the focus is below Earth's surface on the fault plane. Now we measure these waves or these seismic waves with what's called a seismometer. It's an instrument that's used to detect and measure. It's a pin that's attached to a spring and a roll of paper, and it bounces up and down with the waves that's being detected. It's very sensitive, and it detects 3 types of waves. P waves, which are longitudinal, S waves, which are transverse, and surface waves, which are up and down, which are the ones we didn't talk about when we discussed the discovery of the inner and outer core. So measuring an earthquake strength, we have the Richter scale here. There's also the Mercalli scale, but the Richter scale is the one that we are probably most familiar with. The effects of an earthquake are structural damage to buildings. We saw an image of that. Fires, landslide, displacement of land surfaces, tsunamis, and tidal waves. So the Richter scale is based on the swings and the seismograph readings. It's a logarithmic scale, so there's a factor of 10 times stronger between every whole number. So between a 1 and a 2, the earthquake is 10 times stronger. Between a 1 and a 3, it's 100 times stronger. Numbers increase with the magnitude of the earthquake, and it goes anywhere from 3, which is not generally felt, to 9, which is the largest measured so far. And so the thing with scales like this is that sometimes we adjust them as we have bigger and more destructive events occur, but for right now, 9 is the highest we've measured. If we look at the image down here, the Mercalli scale measures things based on damage, so pictures falling off the wall, windows cracked, buildings falling. The problem with the Mercalli scale is that not all buildings were created equal and not all building codes are the same, and so it's kind of hard to judge the strength of an earthquake in Los Angeles, where the building codes are very strict, to somewhere like Missouri that wouldn't have the same building code restrictions with regards to earthquakes. But the Richter scale is more objective because it's measuring the strength based on a seismograph and not based on damage. So we said that sometimes what occurs with an earthquake is a tsunami. So what is a tsunami? Well, it's defined as very large ocean waves. These are not your typical ocean waves coming into shore. They are very tall, very powerful, and the wavelength between them is very, very large, which indicates its strength. Now, tsunamis are generated by a strong disturbance in the ocean floor. So normally an earthquake is going to be the trigger. Whether or not the earthquake occurs on land or under the ocean, that part is not set in stone. The earthquake can occur anywhere, and the tsunami can occur far away from wherever the earthquake occurs. So other things that can generate it are landslides, volcanic explosions. When the tsunami wave comes in, it can reach up to a speed of 725 kilometers per hour, which is roughly 459 miles per hour. The wave height has been measured to be over 8 meters, which is 25 feet. It's roughly a probably 3 to 4 story building, depending on the height of each floor. Very long wavelengths of up to 200 kilometers or 120 miles, meaning one wave would come in and the other wave would be 120 miles away. These are pictures of tsunamis, waves coming into shore. The thing about a tsunami wave is it's going to pour in inland very fast, and it's going to be a very tall wave, so it's going to overwhelm the structures, and it takes a long time for the wave to recede. So sometimes what they'll see before a tsunami hits shore is that the ocean will literally recede. It will come back away from the shore because it's being drawn up, like being sucked up into a straw, into this wave that's forming. So as the ocean recedes, they'll be able to know that there's probably a tsunami wave coming in, because once that water does come in, it's going to pour all the way inland, and then it takes a long time to recede back out to the ocean where it should be. There are a couple of examples of really destructive tsunamis in our recent history, but the most famous one is the one that occurred around Christmas of 2004. There's a movie based on it. It's a very good movie about a family surviving the Indonesian tsunami. And I would recommend it if you haven't seen it. It's a very good testament to strength. And it talks, and you can see a lot of the facts around what happens during a tsunami if you've never seen the effects of it. So we're going to take a break here, and then we're going to come back and talk about origin of mountains, and then finish up the rest of chapter 16.